But yeah, so that's that question. B7. Use partial orbital energy diagrams to describe how the mixing of the atomic orbitals of the central atom leads to the hybrid orbitals in methanol. CH3OH, right? So if we look at methanol and we draw the Lewis structure, right, we have a carbon here, 1, 2, 3, 4, right? That's going to be bound to an oxygen. That's going to be bound to a hydrogen, right? And each one of these carbons is bound to a hydrogen here. And then you have 2 lone pairs on the oxygen right there. And so then if we look at it, right, so that carbon has 4 bonding domains, right? And there's no Lewis structures. So this is going to be sp3 hybridized. We look at this oxygen. It has 2 bonding domains and then 2 lone pairs. And there's no resonance structures that are possible. And so this is also going to be sp3 hybridized, right? And so that means that this is going to be tetrahedral, right? And this is bent in these cases, right? So those are the molecular shapes around them. Now, the next question is kind of trying to tie in what we know about molecular orbital theory and hybrid orbitals, right? When we're thinking about bonding, especially in organic molecules, people love talking about hybrid orbitals, because it helps explain, via CPR theory and explain, how, the shapes and the geometries around atoms. And all, hybrid orbitals are just basically, doing the same thing we would do with MOs, but instead of it doing, making, molecular orbitals between 2 different atoms, we're just simply going with the same atom and we're taking 2 different orbitals and we're mixing them together so that we form new hybrid orbitals that then have, the directionality and shape that we need to maximize, the spacing of our electrons. In our cases. So if we go through this right here, right, fill in the electrons in the diagram and show the resulting hybrid orbital diagram for each atom, right? So if we look at the carbon atom, right, and we fill these in, right, we have 4 electrons total. So we're going to have 2 in the 2s and then 1 in the 2p, or sorry, 2 all alone in the 2p's. If we go to the isolated oxygen atom, right, what we have here is 2 in the 2s and then 1, 2, 3, 4 electrons in the 2p, where one set is paired up, and then you have 2 that are by themselves. So looking at this right here, trying to think about, bonding, to form a bond, like a covalent bond, each electrons are shared, and so you have to have 1 unpaired electron in each atom that can then, come together to form a molecular orbital. But if we look at the carbon, right, we only have 2 unpaired electrons, and so based off of that, we would think, oh well, I can only form 2 bonds, but we all know, right, that carbon forms 4 bonds at least, or not at least, maximum, right, and that has to do with the fact that you have hybrid orbitals that form. And so what happens in the case of hybrid orbitals is that you essentially add up the wave function of the 2s and the different 2p's with different coefficients to kind of, push them in the different directions. And so you end up then with, these all combining together to form 1, 2, 3, 4 sp3 hybrid orbitals, right? So all 4 of those sp3 hybrid orbitals are all degenerate, right? They're all at the exact same energy. And so you're taking the electrons, right, that are in the 2s and you're going to be raising them, but you're going to be taking the electrons that are in the 2p and you're going to be lowering them, so that now, right, when we fill in these electrons and we use Hund's rule, right, we have all unpaired electrons in this case. So all 4 of those electrons are now available to form bonding interactions. So, that's what that right there looks like. Same thing with oxygen, right? Again, we know it's going to be sp3 hybridized, so we're going to get all of these guys mixing together to form 1, 2, 3, 4 sp3 hybrid orbitals. But now, right, we're going to have a total of 1, 2, 3, 4, 5, 6 electrons. So we have 1, 2, 3, 4, 5, 6 electrons in this case. And so looking at that right there, right, that matches pretty closely with what we saw in the Lewis structure in terms of overall bonding and geometry and so forth, right? Because the carbon, right, it has 4 unpaired electrons. It's forming 4 single bonds in those cases, right? In the case of the oxygen, right, it has 2 lone pairs, right, 2 completely filled sp3 orbitals, which we see in the Lewis structure, and it's forming 2 bonds, which we see with the 2 unpaired electrons in those cases. So, that's how hybrid orbitals and MO theory kind of all come together to link up and work together. And so then, right, and that's, basically what we're talking about here for C is, explain what happens during bonding. And so In the case of the carbon, all four of those sp3 hybrid orbitals are forming sigma bonds with the adjacent atoms, right, with the 3 hydrogens and the oxygen. And in the case of the oxygen, right, it has 2 unpaired electrons, so it's forming 2 sigma bonds in those cases, and it has then 2 lone pairs as well that interact. And so that's how they all kind of play in together.